Welcome to another episode of AI 10X brought to you by 10 Leaves.
Glad to be here for this one.
Yeah, if you're anything like me, you probably spend a good chunk of your time thinking about how artificial intelligence is rewriting the code of the digital spaces we inhabit.
Right, the algorithms, the media feeds.
Exactly. But today, our mission is to sort of look up from our screens and focus on the physical world.
Which is a huge shift.
It really is. We're diving into this fascinating set of insights from a source titled Architecting Tomorrow, AI in Construction and Urban Planning. And the goal today is to explore how the literal ground we walk on, the buildings we live in, and the cities we navigate are being engineered and deployed in just entirely new ways.
It's a crucial pivot in how we frame this technology, I think. We are so accustomed to conceptualizing AI as something that exists purely in the cloud.
Yeah, large language models generating text.
Right, or algorithms curating what we see online. But today's deep dive is fundamentally about tangible reality. We're talking about concrete, steel, urban grids.
The physical constraints of human habitats.
Precisely. Seeing computational intelligence translate into physical reality at a massive scale is profound because it shifts AI from a digital tool to, really, an environmental architect.
And to guide you through this, we've got a clear roadmap for our journey today. We'll start on the ground floor, looking at the technical mechanics of the modern construction site and how it's being fundamentally rewired.
The micro level.
Right. And then from there, we'll zoom out to the macro level to examine city building and urban planning. Finally, we'll synthesize all of this to explore the massive benefits of this shift and what it means for the future of our physical infrastructure.
It's a logical progression. And it's important to note the shifts we're discussing aren't theoretical white papers.
Right. This isn't science fiction.
No, these are active, practical deployments altering the fabric of our physical infrastructure right now.
Okay, let's unpack this, starting with phase one, the construction site itself. The materials we're looking at in Architecting Tomorrow point out that AI is actively transforming this environment through robotics and automated planning.
Which are two very different but connected things.
Right, and I want to get past the surface level here. We aren't just talking about a robotic arm swinging a hammer. Help us understand the actual mechanics of what this automated planning looks like on the ground.
Well, to understand this shift, you really have to look at the traditional methodology of construction. It relies heavily on static scheduling.
Like Gantt charts.
Exactly, Gantt charts or waterfall project management. It's a massive, high-stakes logistical puzzle solved through human intuition and buffer time.
Lots of buffer time.
So much buffer time. What the source highlights is a complete transition away from that reactive, manual approach toward high-tech robotics driven by dynamic algorithmic pathfinding.
So what does the robotic site actually look like?
We're talking about autonomous rovers equipped with LiDAR, robotic bricklayers, automated rebar tying machines.
Doing it with sub-millimeter precision.
Exactly.
Yeah.
But the hardware is almost secondary. The real engine is the automated planning layer that directs all of those machines.
Right, because coordinating them is where the actual complexity lies.
Precisely.
So we're moving from static charts to dynamic, algorithmic pathfinding for physical materials. It almost sounds less like traditional project management and more like, I don't know, high-frequency trading.
That's a great analogy.
But applied to supply chains, steel, and concrete.
That is a highly accurate way to frame it. Just think about the variables in a large-scale commercial build.
It's mind-boggling.
You have thousands of distinct material components, hundreds of specialized laborers, and external factors like supply chain bottlenecks or weather.
Right.
Historically, if a shipment of structural steel was delayed by 48 hours, a human project manager would have to manually recalculate how that delay impacts all the downstream dependencies.
The welders, the crane operators, the safety inspectors.
It creates a cascading wave of friction. But with AI-driven automated planning, the system acts like a real-time neural network for the site. It ingests the delay, recalculates the schedule matrix for every worker and machine, and reroutes the workflow instantly to ensure zero idle time.
But how does that actually work in practice? I mean, if a physical site is constantly changing, how does the AI keep up with a reality that's always shifting? Software can recalculate instantly, but moving a crane takes time.
Yeah, that's where the integration of edge computing and sensor fusion comes into play.
Okay.
The AI isn't operating in a vacuum based on a theoretical schedule. It's constantly fed data from the site itself, which ties directly into the next major component the source brings up, real-time monitoring.
Right, because the automated planning algorithm is only as good as the real-time data it receives.
Exactly.
And the source breaks this real-time monitoring down into two distinct pillars: progress and safety. Let's tackle progress first. I'm assuming we've moved past a site foreman walking around with a clipboard to estimate if a floor is 30% complete.
Oh, far past it. The industry standard moving forward relies heavily on building information modeling, or BIM,
I've heard of that.
specifically 4D and 5D BIM, which incorporate time and cost into a 3D spatial model.
Wow.
What the AI does is utilize autonomous drones and fixed cameras to constantly scan the physical site. It generates massive point clouds using LiDAR and photogrammetry.
So it's mapping the space in real time.
Right. The AI then overlays this real-time 3D scan of the physical build onto the digital twin, the perfect digital blueprint, and compares them down to the millimeter.
So it's essentially running a continuous check, like,
Like version control.
right, like Git version control, but for a physical skyscraper. It spots any deviation between the code, the digital twin, and the actual building.
Precisely. If a concrete pour is off by 2 centimeters, or if an HVAC duct is installed slightly out of alignment, the system flags it immediately.
It doesn't wait for a human to notice.
It doesn't wait for a structural inspection 3 weeks later, when fixing the error would require tearing down drywall and rewiring electrical systems.
Which is a nightmare.
It identifies the spatial discrepancy in real time, allowing for immediate course correction. This eliminates the massive sunk costs associated with rework.
That makes the financial and efficiency implications totally obvious. But let's pivot to the second pillar of this real-time monitoring safety. A construction site is inherently hazardous. You've got heavy machinery, dynamic environments, suspended loads. How does AI monitoring move the needle on safety beyond just, recording an incident on camera when it happens?
The key transition here is from reactive to predictive. Traditional safety protocols are largely reactive.
You train people, you put up barriers.
And if an accident happens, you investigate after the fact. The source material emphasizes that an AI-monitored site operates as a ubiquitous predictive safety net. Yes. The system utilizes computer vision to constantly analyze video feeds across the entire environment. It's trained to recognize complex spatial overlaps and stress vectors before a human spotter ever could.
Let's push on that a bit. What does a spatial overlap or stress vector actually mean in the context of a worker on the ground?
It means the AI is calculating trajectories. If it detects a human worker walking on a path that will intersect with the blind spot of an autonomous vehicle in 5 seconds, it doesn't wait for them to collide.
It anticipates it.
It can instantly throttle down the autonomous vehicle or trigger a localized alert.
That's incredible.
Furthermore, if it's monitoring a temporary load-bearing support structure, it can analyze micro-deformations in the material using high-resolution sensor data.
So if it's bending even slightly.
If the temporary support is bowing by a fraction of a degree that indicates dangerous stress, the AI recognizes the anomaly and halts operations in that sector immediately.
So the environment itself is actively engaged in hazard detection. Think about the implications of that for a second.
It's huge.
The cognitive load required for sheer physical survival is massive in manual labor. By delegating that ambient spatial awareness to an AI, you're fundamentally changing the psychological baseline of the workforce.
You really are.
They can focus on precision execution rather than constantly scanning over their shoulder for rogue machinery or failing supports.
And that reduction in cognitive fatigue directly correlates to higher quality work. The site transforms from a chaotic environment requiring brute force and constant hypervigilance into a highly synchronized, tightly controlled ecosystem.
It behaves more like an advanced manufacturing floor than a traditional dirt and diesel construction site.
Exactly.
Here's where it gets really interesting, because architecting tomorrow doesn't just stop at individual building sites. If we take that clean room level of precision we just talked about and scale it up to the size of a whole neighborhood, that's where the source material makes a massive pivot into macro-level urban planning.
Yes. Scaling this technology up to the level of entire cities introduces an exponential leap in complexity. At this macro level, the primary mechanism the source identifies is AI simulation. Before a single excavator is deployed, planners are utilizing hyper-complex simulations to optimize 3 specific pillars of city building:
And those are?
urban layouts, energy systems, and infrastructure planning.
Let's break those down, starting with urban layouts. We're obviously far beyond basic zoning maps with colored blocks here. When an AI simulation is tasked with optimizing a layout, what parameters is it actually manipulating to find the optimal design?
It's utilizing parameter-driven generative design. When human urban planners design a district, they're limited by the number of variables they can juggle simultaneously.
Traffic flow, zoning laws, basic topography.
Right. An AI simulation, however, uses algorithms to run millions of iterations of an urban layout against a highly complex fitness function.
Millions.
Millions. For example, it can calculate the exact solar gain of every proposed building. It can model how the placement of a 40-story high-rise will create wind shear or alter the microclimate of the streets below it.
So it's literally mapping out computational fluid dynamics to ensure pedestrian walkways aren't turning into wind tunnels,
Yes.
while simultaneously ensuring that public parks receive the optimal hours of direct sunlight year-round. That's wild.
Exactly. It can dynamically shift the orientation of buildings, the width of thoroughfares, and the distribution of mixed-use spaces until it finds the mathematical optimum for human livability and efficiency.
Before a single brick is laid.
It simulates the lived experience of the environment across decades of potential weather patterns and traffic conditions.
Which feeds perfectly into the second pillar, energy systems. A city's energy grid is incredibly volatile. You've got legacy power plants, decentralized solar arrays, and thousands of buildings drawing power in highly unpredictable spikes.
It's a very delicate balancing act.
How does AI simulation tame that chaos before the grid is even built?
By designing for dynamic load balancing and treating buildings not just as passive consumers, but as active nodes in a virtual power plant.
Virtual power plant.
The AI simulates the energy consumption of an entire proposed district under extreme stress tests.
Like protracted heat waves.
Heat waves, deep freezes, sudden economic shifts. It allows planners to design smart grids capable of bidirectional communication.
Meaning the grid doesn't just push power out, it actively negotiates with the infrastructure.
Right. If the simulation shows that a specific commercial sector will experience a massive power spike every weekday at 2 p.m. during the summer, the AI designs the system to preemptively store surplus energy generated by residential solar panels during the morning.
Oh, wow.
And then it automatically routes it to the commercial sector right before the spike hits. You effectively shave the peak off the demand curve.
Which is huge.
It eliminates the incredibly wasteful legacy approach of building massive carbon-heavy peaker power plants that only turn on for a few hours a day.
That's a massive leap in resource management. And it leads us to the third macro element, infrastructure planning. We're talking about the arteries of the city: water, waste, transit networks, bridges.
If we connect this to the bigger picture, the reason simulating infrastructure is so critical comes down to the cost of permanence.
The cost of permanence.
In the digital world, if you deploy bad code, you can push a patch in an afternoon. In the physical world, if you undersize a subterranean sewer system for a population that grows 20% faster than expected,
Or if you build a highway interchange with an inherent bottleneck.
you are locked into a billion-dollar failure that might take half a century to rectify. Infrastructure is stubbornly, expensively permanent.
So the AI acts as a digital stress test against that permanence. It allows urban planners to fast forward the simulation, hitting the infrastructure with predictive climate models, demographic shifts, and autonomous vehicle integration scenarios.
It's essentially the end of the trial and error era of city building. The AI can find the failure points in the transit network or the water reclamation system digitally, allowing engineers to redesign for resilience before any concrete is poured.
I want you, listening right now, to just imagine living in a city where the layout and the energy grids were perfectly optimized by AI before they were even built. No awkward traffic bottlenecks, no dead zones.
It's a completely different standard of living.
So what does this all mean? We've unpacked autonomous rovers utilizing LiDAR, edge computing safety networks, and generative design algorithms running millions of urban layout iterations. When we distill all this technology down, what is the ultimate payoff for the industry and the physical world?
The source material synthesizes the outcome of these intersecting technologies into three definitive benefits: faster builds, lower costs, and smarter cities.
Faster, cheaper, and smarter. Anyone familiar with project management immediately recognizes that as a direct challenge to the classic iron triangle.
Right.
The old rule is good, fast, cheap, pick two. If you want it fast and cheap, quality suffers. If you want high quality and speed, costs skyrocket.
What's fascinating here is how the introduction of AI fundamentally breaks that iron triangle. Historically, those three constraints were constantly in friction because human execution is inherently variable.
Yeah.
You had to build in massive time buffers to account for mistakes, which drove up costs. You had to compromise on design complexity to ensure it could actually be built on time, which lowered the smartness or quality.
But because the automated planning eliminates the logistical downtime and the robotics execute with sub-millimeter precision, that buffer time is essentially erased.
Exactly. The builds are vastly faster because the sequence of operations is mathematically optimized and executed without the friction of human logistical bottlenecks.
And speed is money.
That speed directly compresses the schedule, which drastically lowers the capital costs associated with long-term labor and equipment rentals. Furthermore, the real-time BIM monitoring we discussed earlier eliminates the cost of rework.
Which is one of the largest financial drains in traditional construction.
Unquestionably.
And crucially, this speed and cost reduction isn't achieved by cutting corners on the materials or the design. The quality is actually elevated, leading to that third benefit: smarter cities.
That is the ultimate synthesis. AI enables all three simultaneously because the physical build is merely the execution of a perfectly optimized digital simulation.
The building already succeeded digitally before it existed physically.
The resulting structure isn't just a cheaper, faster building. It's a highly efficient node, integrated seamlessly into an intelligently planned urban grid. It maximizes thermal efficiency, balances its own energy loads, and interfaces flawlessly with the surrounding infrastructure.
It totally redefines what the construction industry is at its core. I mean, for generations, construction has been categorized as a brute force, glue-collar endeavor. It was about moving massive amounts of material from point A to point B through sheer physical exertion and reactive management.
A very analog process.
But looking at the insights from Architecting Tomorrow, that entire paradigm is obsolete. Construction is now a precision engineering discipline. It's fully crossed over into being a tech industry.
It's the ultimate manifestation of digital intelligence imposing optimal order onto physical reality. The raw materials, the steel, the glass, the concrete, are still the foundation, but they are now enveloped in a highly connected, deeply intelligent technological ecosystem.
Wow.
The physical world is becoming as programmable and optimizable as the digital world.
It's a staggering shift in how we approach the built environment. We started this deep dive with a mission to explore how the physical world around us is changing, and the takeaways are undeniable. Construction is no longer just about hard hats and blueprints.
Far from it.
From real-time point cloud scanning on the job site to algorithmic load balancing across municipal power grids, artificial intelligence is the new bedrock of our infrastructure. It's rapidly evolving into a high-tech, AI-driven industry.
This raises an important question, one I think is worth analyzing as these technologies scale.
Okay, lay it on us.
We focused heavily on the mechanics of optimization, generative urban layouts, frictionless logistics, predictive safety monitoring. But cities are fundamentally habitats. They are the arenas where human lives play out.
Right.
So, if AI is successfully modeling and aggressively optimizing our urban layouts, energy systems, and infrastructure to build smarter cities, how might that ultimately change the way you, the listener, experience and move through your own city in the future?
That's a great point.
How will the human experience evolve when every street, shadow, and transit line has been pre-calculated for optimal performance by an intelligence far beyond human intuition?
That is a profound angle to consider. A mathematically optimized physical reality, and what happens to the spontaneous, maybe even chaotic human element within it. Thank you for taking the time to unpack all of this with us today. We love exploring these complex systems and uncovering the hidden mechanics of the world with you. This was AI 10X, brought to you by 10 Leaves.